Hi, this is Candace. I'm doing this video today, if you find this useful, on the dimensional analysis PowerPoint for students to go over some of the math. At any time while you're watching this video, going over this PowerPoint, or doing the practice problems that are posted on Canvas, and you're having any problems with any of the problems, please feel free to email me and I'd be more than happy to go over that problem with you one-on-one. So you want to use dimensional analysis when you're setting up your math problems. It's the most reliable way to do that. I do realize that some of you can do math in your head, lucky you. But if you can't do math in your head, you definitely want to use dimensional analysis to make sure you have the problem set up correctly. It's kind of a security blanket. So for example, let's say we have ondansetron, another name for that is Zofran, 5 milligrams IV push. What you have is Zofran 2 milligrams per mil. How much will you draw up? So according to the rules of dimensional analysis, you want to put what you're calculating on the left side of your equation. So what is it that you're calculating here? Good. You're going to draw it up into a syringe, so what you're calculating is milliliters. So you're going to put milliliters on the, is that big enough? You're going to put milliliters on the left side of your equation. And then what's on the numerator needs to match this. So what's here that's milliliters that's going to match this? So we have mils that's tied to our 2 milligrams. So milliliter is going to go on top. 2 milligrams is going to go on the bottom. And then we want milligrams to go on top here because that's going to cancel out milligrams. So what you have ordered is 5 milligrams. So 5 milligrams is going to go on top. So then this is just what I like to do when I was a student and even as a nurse today, is I would cross off what cancels, our milligrams are going to cancel, and circle what stays. And that's how I know if it's set up correctly, because mils match mils. So I know I have the problem set up correctly. Now I just need to do the calculation. And when we do that, 5 divided by 2 is 2.5 milliliters. Now when I do math, the more math that I've done as a nurse, it makes sense to me why it's set up that way. But there are still times where it doesn't make sense to me why it's set up that way, but I follow the rules of dimensional analysis, and then I know this matches what I'm calculating. Even though I don't understand why it's set up that way, I know I have it set up correctly according to dimensional analysis to get to the correct problem. So 2.5 mils, you want to keep it at 2.5 mils because what you're giving, so if you were to round that up to 3, that's more than 2.5 mils. So when you get to 2.5 mils, what you're drawing up is 2.5 mils, not 3 milliliters. So be careful not to round up with that because you could potentially be giving more medication than what's actually ordered. So another problem is, let's say you have Reglan, and this is actually a problem from 4th quarter, especially when you're giving Reglan to a child, you're not going to give the same dosage that you would to an adult. So when we get down here, it's asking how much will you draw up? So what is it that you're calculating? Good, you're drawing it up into a syringe, so what you're calculating is still milliliters. So what I like to do is I like to take the 0.2 milligrams per kilogram and the weight of the person, and to calculate that off to the side and then plug it into my equation. But you can certainly plug it into your equation too, whatever is easiest for you. So what I do off to the side is I'll take 0.2, multiply that by 36, and you get 7.2 milligrams. So I have that just off here in a holding pattern, and then I'm going to start setting up my dimensional analysis. So what goes on top here needs to match here the mils. So what's in your problem where you see mils? You see it right there. So milliliters is going to go right on top, and that's attached to 5 milligrams. So 5 milligrams is going to go on the bottom. And then I'm going to plug in my 7.2 milligrams, put it right here. And again, I like to cross off what's going to cancel out and circle what stays, and mils match mils, so I know I have it set up correctly. And the answer is 1.44 when you do the calculation. And then we want to round this to the 10th, so this 4 being the 10th spot. If you round this to the 10th, what do you get? Good, 1.4 milliliters. So because this is under 5, this stays the same. But if this were 5 or higher, then you would round up. So if this were 5, this would round to 1.5. But because this is under 5, this stays at 1.4 when we round to the 10th. So do you remember back in third quarter when you have an IV pump that's in your question, and I said to tattoo this to the gray matter, that when you have an IV pump, it's always going to be mils per hour. So remember, you tattoo that to the gray matter, but you might not have a pump, and you're going to have to do a drips per minute rate. So we do a drips per minute rate when we don't have a pump to actually regulate the infusion. And again, remember, pump is mils per hour, but if we're not using a pump, then it's going to be drips per minute. And we have micro and macro tubing. In the math problem, if it's going to be a drips per minute, you're always going to get what the drop factor is for your tubing. So micro tubing at 60 drops per mil. Macro tubing can be 10, 15, 20 drops per mil, but you're going to get that in your math problem. In practice, if you need to set up a drips per minute, you would find the drop factor for the tubing or the drops per mil. You'll find that on the actual packaging of the tubing. So let's say you're on an overseas trip. You might remember this problem from third quarter when we were doing the IV skills lab and I was going over math. This is one of the problems I did with you guys. So you're on an overseas medical trip, you need to run normal saline at 150 milliliters per hour, but you don't have any pumps available. So there are no IV pumps. You have macro drip tubing, which is 15 drops per mil, the drop factor for the tubing. What is the drip rate? Since we don't have a pump, what we're calculating is drips per minute. And now this, the numerator needs to match this. So what do we see here that matches that? 15 drops. So 15 drops is going to go on the top, and there's 15 drops per mil. Mil is going to go on the bottom. And 150 mils per hour. An hour will go on the bottom. Now let's say if we cancel out mils, we have drips per hour. Does that match drips per minute? No. So we need to carry that out. And have hour that cancels out, and our minutes stay. And again, I always just like to circle what stays. Drips per minute, match drips per minute, and that comes out to 37.5 drips per minute. And since we have IV fluids here, normal saline, it's a lot easier just to round that up. And what would this round up to when we round up to the whole number? Good, that would round up to 38 because this is 5 or higher. If that had been a 4, what would that round to? Good, that would round to 37. So on the math test, if you leave it at 37.5 or you round it up to 38, you're going to get credit for both. Okay. And just on this one is just paying attention to when your IV is going to finish infusing. So if it's going to infuse over 8 hours, pay attention to that. There's things that can happen, such as your IV pump has been unplugged and then the battery went dead, and if it's been 8 hours but you have half a bag left, just to kind of pay attention to those things. So that's what this slide there is about. And then we're looking at calculating IV medication drip rate, especially when we look at heparin, cardizem, nitroglycerin, dopamine, titrating, all of that good stuff. So we're going to go over some practice problems with that. Okay, so for example, the doctor's ordered cardizem. And what is cardizem classified as? It's a cardiac med, just to review. Good, that's a calcium channel blocker. Anyway, so cardizem IV drip at 10 milligrams per hour. Pharmacy sends you cardizem 200 milligrams that's in 250 milliliters. I should have added normal saline here, but 250 milliliters of normal saline. What is the infusion rate? So we're definitely going to use a pump to infuse this. So if we're using a pump to infuse this, what is it that you're calculating? Good, mils per hour. So numerator, this needs to match this. So what's in your problem that matches mils? So there's 250 milliliters. I'm going to put that on top. And the 250 milliliters is attached to the 200 milligrams. That's going to go on the bottom. And then 10 milligrams is going to go on top here. So we want that to cancel out, 10 milligrams per hour. And when I cross off milligrams, and then I circle mils per hour match mils per hour. So I know I have it set up correctly. And when I do the calculation, you get 12.5 milliliters per hour. And here, you want to keep it at 12.5 mils per hour because this is a cardiac drip. We don't want to round that up to 13 because they're going to get more of that cardiac drip rate, and that wouldn't be a good thing. So you want to, when you get to 12.5, so things like heparin, cardiac meds, all of that, when we're giving drip rates, we want to keep it where it's at. So, but on the test, if you round that up to 13, I will still give you credit for it. I just want to caution you on that with cardiac meds. We don't round up with that. Okay. And then continuing with drip rates, especially when you have to calculate in their, or factor in their weight with that, and looking at micrograms with that. We're going to go over some practice problems for that. So, for example, we have dopamine that's ordered, IV drip, 5 micrograms per kilogram per minute. Patient weighs 191 pounds. And what you have is dopamine, 300 milligrams, that's in 250 milliliters of normal saline. At what rate will you run it? Now, we're going to be using a pump to calculate this problem. So when you're using a pump, what is it that you're calculating? Good. Pumps are always mils per hour. So we're going to be at mils per hour. But as far as our micrograms and our weight and all that, I like to get that taken care of and put that off to the side and then plug it into the equation. If you like to plug it into the equation from the get-go, you can do that, just whatever you're most comfortable with. So we're going to convert 191 pounds to kilograms. So what are we going to divide 191 pounds by? Good. We're going to divide that by 2.2. So we take 191, divide by 2.2. We get 86.8 kilograms. And then I'll take the kilograms and multiply that by the 5 micrograms. So times 5 micrograms, and we get 434 micrograms per minute, and I just keep that in a holding pattern until I'm ready to use it. And then I'm going to come back to my dimensional analysis. So we want mils per hour because we're using a pump and it wants to know what you're going to run it at. So the top one is going to match the mils. So we're going to find our mils, 250 milliliters. That's going to go on top. And 250 milliliters is attached to 300 milligrams. So that's going to go on the bottom. Now we do need to convert, because micrograms doesn't match milligrams, and we want milligrams to cancel out. So how many milligrams, this is a conversion factor to put in there, how many milligrams is there for, how many micrograms in 1 milligram? So there's 1 milligram per 1,000 micrograms. I'm going to plug that in. And we have, then we're going to plug this into 434 micrograms per minute. Let me put my glasses on here. And then then we're going to keep it coming across here, sorry. So, and let me just kind of rewrite this so I get it all the way across the board. So we want milliliters per hour equals, and the 250 milliliters, because this matches that. And that 250 milliliters is attached to 300 milligrams. And now we have to do our conversion factor, the factor in the micrograms. So we have 1 milligram, because we're canceling out milligrams, 1 milligram per 1,000 micrograms. Then I'm going to plug in my 434 micrograms per minute. And then you can't stop it here because it's not per minute, it's per hour. So 60 minutes over 1 hour. So I'm just going to go cancel. So cancel milligrams, milligrams, micrograms, micrograms, minutes, minutes, and what's left is mils per hour. I like to do this off to the side and then plug it in. You can plug it in from the get-go. For me personally, it just makes it really unruly to have it there. So when you multiply across, you can certainly reduce to, that makes your math easier, but let's say we multiply all the way across, we get 6,510,000. And then divided by, multiply that across 300,000, and you come up with 21.7 milliliters per hour is the correct answer. And again, dopamine, and just to review, what is dopamine classified as? That's a sympathetic classification of cardiac meds because it's going to mimic the sympathetic nervous system. Again, it's a cardiac med, so we don't want to round that up. We want to keep it at 21.7 mils per hour, not round that up to 22. And then you can see problems too where it might be ordered 6 to 10 micrograms per kilogram per minute, where you have a range where you can kind of decide where it's going to be at. For example, when we give nitroglycerin, we can titrate it depending on what the blood pressure is doing. So when you calculate this problem, you want to calculate for what the lower range is and then calculate for what the high range is to know what that is. So for example, the order is 5 to 10 micrograms per kilogram per minute. Patient weighs 79.6 kilograms, and the med you have is 100 milligrams. That's in 40 milliliters of solution. So for example, I like to take my off to the side, so let's say start with the low, take the 5 times 79.6, so 5 times 79.6 equals 398 micrograms per minute. And then 10, the high range, 10 times 79.6 kilograms, the weight, equals 796 micrograms per minute. So our range for micrograms per minute is 398, being the low range, to 796 micrograms per minute, being the high range. So now we want to know what is the range of the flow rates, or what we're going to infuse that for the IV pump, which would be the milliliters per hour. So I'm going to start with the low range for the milliliters per hour. So this numerator needs to match the milliliters. So we're going to find in our problem where the milliliters are, and that's right here, 40 milliliters. And then 40 milliliters is attached to the 100 milligrams, and that's going to go on the bottom. Again, we have to do the conversion because we have micrograms, so micrograms to milligrams. So there's milligram's going to go here, so there's 1 milligram per how many micrograms? Good, 1,000 micrograms. And so doing it for the low one, I'm going to plug this one in first. I'm doing the low first, so 398 micrograms. Per minute. And again, it's going to be per hour, so we want to carry that out. So there's 60 minutes in 1 hour. So when I cancel out milligrams, micrograms, minutes, left with mils per hour, and that comes out to 9.552. And this one we are going to round, so that's going to go up to 10 milliliters per hour. So 10 is our low range, so starting at 10 milliliters per hour. And now we're going to calculate for the high range, which is 10 micrograms. I'm going to erase that. But again, what's going to go on top here is still 40 milliliters, because that matches that, milliliters, and the 40 milliliters is still attached to 100 milligrams. And we still need to convert, so 1 milligram per 1,000 micrograms. But now we're going to plug in our high range, which is the 796 micrograms per minute. And then 60 minutes for 1 hour. And then cancel milligrams, cancel micrograms, minutes, mils per hour, match mils per hour. And when you do the calculation for that, you get 19.104, and we'll round that to 19 mils per hour. So our range goes up to 19. So they can go from 10 milliliters per hour to 19 milliliters per hour, and that's how we're titrating that. And they'll have specific parameters. For instance, if you're doing a nitroglycerin drip, that might say if the blood pressure is greater than 100, but it lowers by this much, you can go up by 1 or go down by 1, but this would be your range there. Okay, so this is actually a problem from the practice problems or practice tests that's posted on Canvas. So just kind of applying this stuff. So your patient is receiving nitroglycerin, 75 milligrams in 500 milliliters P5W. You have the IV pump set at 20 mils per hour, how many micrograms per minute is the patient receiving. So it's actually telling you what it is you're calculating, or what needs to go on the left side of the equation. So we actually need to know micrograms per minute, because that's what it's asking for. So, micrograms per minute. So this is where we're going to actually be starting off with our conversion factor. So you want micrograms to match this. So there's 1,000 micrograms in 1 milligram. And then we want the milligrams on top of here, because that's going to cancel out. So we're going to find our milligrams in here. There's 75 milligrams and 500 milliliters. So 75 milligrams is going to go on top here, 500 milliliters on the bottom. And then we want mils to go on top here, because mils is going to cancel out. So we have 20 milliliters, and that's attached to hour, so per hour. Now we're not done, because we want micrograms per minute. We're going to carry that out 1 hour. So this is going to cancel out over 60 minutes. So milligrams cancel out, milliliters cancel out, hour cancel out, and you're left with micrograms per minute, micrograms per minute, match micrograms per minute, and you come up with 50 micrograms per minute is your answer for that. So for the test, no dimensional analysis, well, again, if you can do math in your head and you get the right answer and you don't show me any math, you're still going to get credit as long as you get the right answer. But doing the, showing your work and doing dimensional analysis really helps me to see where you went wrong or what have you. And also dimensional analysis is a way to make sure that you have it set up right and it's a reliable method to use. But again, there are different ways to set it up, so you do what works best for you. If you, as far as all the practice math tests or the practice tests that are posted on Canvas and then going over this video and the PowerPoint and all of that, if you do all of those and do those well, you're going to do just fine on the math test. I do know that there, in your math book, there are some discrepancies or not always the correct answer and stuff. So, but I would just focus on the practice tests that are posted on Canvas. I have the answers there too. But if there's any problems that are really tripping you up, again, feel free to email me, and I'd be more than happy to sit down with you one-on-one and go over that. Remember your conversions. So, and I have those posted on Canvas. So one conversion, for example, there's 1 milligram per 1,000 micrograms, but also remember teaspoons, 2 mils, 1 teaspoon per 5 mils. Remember those conversions, because you'll need those for the math test or when you're in clinical and you're calculating a problem. So for the math test, you could have some stations set up where I might have some IV fluids that are hanging, and that's part of the problem when you're looking for your information, just like you would in clinical if you had an IV bag and you had to do your math problem. When you do the math test, I will grade it right on the spot, so when you're done, I will grade it for you. If you didn't get the 90%, I will then kind of go over that with you and have you go back and redo those problems until you get all those answers right. So before you leave the math test, you will have already remediated that too. So if you get, let's say 85% on the test, so that when you take it, that's what's going to go in a grade book. But I'm going to have you go back and recalculate some of the problems that you missed, and we'll get that taken care of so you have that remediated when you leave, before you leave the math test. that's it. So thank you for watching this video.